So we will see now why the box topology is not nice. I'll give an example to say that it's a bit pathological. For this, we'll need to take a specific product, and so I'll take the product over natural numbers of let's say the real numbers. Okay, and so this is, well, it's sequences x1, x2, xn onwards, infinite sequences where xi are in R. So with these sequences we have, well, remember what the open sets are. This is the naive generalization from finite dimension. They're u1 cross u2 cross so on, the product un with uj contained in are open for all j. Okay, that's fine. So let's look at some specific sequence. Okay, so let an be the sequence which is given by 1 over n, etc., 1 over n. And a infinity is, you can guess, 0, 0, 0 onwards. Clarify, this is not finite, it goes on forever. It's 1 over n. Okay, so then the claim is or I can call it proposition, something you would always expect, which is an converges to infinity, is not true for the box topology. And the reason is quite simple. We can make the UNs smaller and smaller very rapidly. Okay, so namely, consider the open set, neighborhood of 0, 0 of a infinity, which is 0, 0, given by, let me write out, minus 1, 1 cross minus half, half cross minus 1/3, 1/3, and you get the idea. So at the nth position it's minus 1 over n, 1 over n. These are getting smaller onwards. Okay, then for all n, so I should give this a name, an does not belong to u as the nth component. Sorry, I will look at the n plus first component. Component of an is, so this is u, is this. Let's call this u1, u2, etc. N plus first component of an is like any other component, 1 over n, but un plus 1 is minus 1 over n plus 1, 1 over n plus 1, and 1 over n is not in this set. So you have to be eventually in this set, but you are never in this set. And so you don't converge to 0. So this is where you have too much freedom in having sets, allowing separate sets at each level. Okay, so there are too many open sets. It means convergence becomes very rare, and continuity of functions to this box topology is too rare. You can kind of guess from this what is the topology. Essentially what will have to happen is, after finitely many stages, you'll eventually have to become equal to the value and stay equal to the value. If there's any room at all, you can squeeze in an open set between the two and avoid converging. So this is clearly a problem. So this sort of rules out the box topology. Now we have shown the product topology is nice in that it's the initial topology with the projections, and it also has a property in terms of continuity of functions. We'll somewhat upgrade that property next, that is to justify further why the product is correct. For this, we'll sharpen further. Rather than just having a topology on a given set, we'll just say that we have to be given a topological space. So given spaces X alpha, alpha in A, the product, well, so far it's not the product is, well, a topological space product alpha in A X alpha. We know nothing about this so far. It's just some topological space. Continuous maps P alpha, which map product. Well, let me put a beta here because I said alpha x beta to x alpha for all alpha in A. So we have projection maps from this product such that something happens. So these are continuous such that given Y topological space, I put it on separate lines, such that if we are given Y, this is a topological space, and functions f alpha, which will map Y to x alpha, there exists a unique continuous map f from Y to the product to of x beta, I just wrote it their way, such that for all alpha in A, f alpha is p alpha composed with f. So there's a unique map which combines all these together. Okay. So we have already seen this is true. We have seen that the universal that the space satisfies this property. Important thing to note here is that we did not specify this even as a set. This is stated completely in terms of just continuous maps, that there is a space, something appropriate, and continuous maps, so that given another space and certain maps, you get a unique solution to having this kind of map. Now this is a universal property. It's very useful to note that if we replace topological space throughout by say groups, we get a product of groups, or vector spaces, we get a product of vector spaces. So, and you of course have to replace continuous maps by homomorphisms or linear transformations appropriately. And the proposition is that if such a space, if the product, or rather given two products, so there are spaces, so let me call them P alpha in A X alpha and maps P alpha, and let me say another thing, alpha in A X alpha. And so if suppose I had a product, this is the usual product, and I have another way of constructing a product which I say satisfies the same property. Okay, so P hat X alpha, and then I have P alpha hat. So a product is not just a space, an object, but space together with a collection of maps. So given two products satisfying the above, there exists a homeomorphism. So these are homeomorphic. So there exists a homeomorphism. Let me call it phi from the first product, X alpha to the second product, X alpha, such that I'll just say compatible with P alphas. With P alpha hat. So since this is really just illustrative, we are not going to use it. I won't spell it out. It means that some various compositions of phi with P alpha hat is going to be P alpha. That will become evident from the proof. The proof is by universal property. Okay, so this is a product. Yeah. So using, or let me be specific. So taking Y as product of alpha in A of X alpha, and F alpha is the projection maps P alpha in the universal property for the pi hat X alpha, we get, what do we get? Well, we have a collection of maps all mapping to X alpha from this product. So we get a single map to the product, but this is the hat product. So we get phi mapping product of alpha in A X alpha, such that if I look at P alpha hat composed with phi, this is P alpha. Okay, by the way, this is what the compatible with phi will look like, but we don't yet have a homeomorphism. That's the main thing. But the thing is, this is symmetric, so we can actually reverse the rules. Yeah, so it's maybe worth going through half a page and keeping that here. So now let's taking now y is this time pi hat of X alpha. F alpha is P alpha hat. So reversing the rules, we get a map C, which maps this time the product hat of alpha in A of X alpha to the usual product alpha in A X alpha, such that this time what happens is that if I look at they stitch together the maps P hat alpha. So this means that P alpha composed with Psi. So let's check the direction. Psi is going to take your pi hat to pi, and so P alpha does compose with it. This gives me the given maps P alpha hat, which were the F hat. Okay. So what happens is, now let's look at the composition. So hence, let's look at Psi composed with phi. Okay, so phi is going to take this product to its product. So this will take product alpha in A of X alpha to product in A of X alpha is a continuous function. Such that when we put these two together, so P alpha composed with C, such that we will see that if you look at P alpha composed with C composed with phi, it's probably P alpha hat. So P alpha, no, yeah, P alphas, this is equal to P alpha. Why is that? Because P alpha composed with C is P alpha hat, and P alpha hat composed with phi is P alpha. Okay, so this is in two steps we see such that this happens. Oops. Okay, so we are in good shape now. What we have is we have maps. So what can we say about C composed with phi once we have all this about it? Okay, so we can see that if we look at, I won't write out the proof, it's using those two earlier equations. Okay, so now that we have this, but now, so what happens here? So thus, you can say C composed with phi is, so corresponds to the universal property. So we are going to call these F alphas. Okay. And phi has this as the domain, but I'm going to treat this as Y. So universal property for the product, the ordinary product, alpha in A, or standard product, with F alpha equals P alpha, and Y is this thing itself, product alpha in A of X alpha. So what you need is a map C composed with phi, so that when you compose it with P alpha, you get the maps P alpha themselves. So this guy is going to be F alpha, projection composition with P. But there is another but identity of the product also corresponds to this. So corresponds to, or you can think of it as solving, also solves the problem. Okay, so also corresponds to the same. Same y and f alphas. Namely, what is the condition we need? We need p alpha composed with identity is p alpha, which is of course true. So identity also do. By uniqueness, so remember this is the crucial point we have assumed. We have assumed not only does an f exist, but it has to be unique. If it doesn't unique, you could have lots of extra stuff in the product, which is never detected by projections. So by uniqueness, well, this and this are both solutions to the same problem. So by uniqueness, C composed with phi is the identity. Okay, and I'm going to omit who the identity is. And similarly, phi composed with C is the identity. This will be the identity on the other set. So thus, phi is a homeomorphism. So you have continuous functions which are inverses of each other. So phi is a homeomorphism as claimed. So the moral here is that in many cases, if you set up the properties correctly, and it is always of this nature, there is a space, there are functions, so that given some other space and some other appropriate functions, you get one or more functions, so that various compositions are as prescribed. Now if this is set correctly, there is a solution and the solution is unique. And the uniqueness can be proved without showing it exists at all. So we never use the nature of the product here. We simply use the universal property. So this is a very powerful way to think about things. And the product is also correct because it is in this sense a product. What would in mathematics generally be called a categorical product. So as I said, this has counterparts simply by replacing topological space by vector space, group, abelian group, module, whatever you like, whatever is your favorite structure, and then continuous map by the appropriate homomorphism, linear transformation, whatever else is appropriate, you will get a corresponding notion of product in some other situation. So that is the so this justifies in another way this as the correct notion of product.